Hello everyone, I'm Yupeng, and today I'm excited to present our work on minimally constrained multi-robot coordination with line-of-sight connectivity maintenance. A network multi-robot system is a collection of multiple autonomous robots, and the robots can communicate and collaborate with each other to accomplish complex tasks more efficiently and effectively than a single robot could do alone. For example, in a multi-robot system consisting of both ground robots and aerial drones, if they are within the communication range, these diverse agents can effectively collaborate and communicate with one another to execute field exploration tasks. In order to maximize the effectiveness of communication in a multi-robot system, it is essential to ensure connectivity at both global and subgroup levels. This includes maintaining global connectivity across the entire system, as well as maintaining communication within each subgroup. The robots in the same subgroup may perform similar tasks, but maintaining subgroup connectivity, they can communicate with each other directly instead of wasting unnecessary information exchange. This well-defined networked multi-robot system can be adopted in various applications, such like agriculture, urban search and rescue, and so on. However, Pierre's work mainly focused on maintaining regular communication, with the assumption that two robots can effectively communicate as long as they are within a predefined communication range. In many real-world scenarios, it is essential to consider line-of-sight connectivity, which goes beyond simple range-based communication by ensuring that there is an unobstructed path for information exchange between robots. For example, given those robots which are connected with Wi-Fi signals, these robots can communicate with each other and execute the field exploration tasks efficiently. But if there are obstacles blocking the communication edge, they will easily lose communication. If the obstacles are made by the metal, the wave-based signal will easily be blocked by the obstacles, which cause robots to lose communication with each other and hence fail to perform tasks. With the basic introduction and the motivation mentioned above, we here introduce our work's objective, that is minimally constrained multi-robot coordination. Given a task-related controller UI height, the basic demand is that we seek to minimally modify it, that satisfying the safety control constraints and develop line-of-sight connectivity control constraints. Given the robot position, we are able to acquire the line-of-sight communication graph, which are represented by pink edges. Maintaining unnecessary edges will introduce more motion constraints on the robots. Hence, we may want to select the optimal graph, which is represented by the red edges to maintain required connectivity. By jointly optimizing the communication edges to maintain representing the motion constraints and their effect on the nominal controller, thus enable the flexibility of the coordination. With this, the design control revision strategy can provide flexible coordination for the robotic team to execute tasks efficiently. Finally, the design control revision strategy can be applied in a large-scale system and be computed efficiently. Next, I'll talk about our method. Our method is implemented at each time step. The line-of-sight connectivity is preserved when the previous robots are within the communication range and the communication edges are not isolated by the obstacles. Hence, we develop the line-of-sight connectivity barrier certificates using control barrier function that define the admissible control space for maintaining the previous inter-robot line-of-sight communication edge in any given graph line-of-sight connect over time. Then, we'll talk about how to extract the optimal graph from the current line-of-sight communication graph. The optimal graph must have the following properties. It must have the minimum number of edges to maintain. It must be global and subgroup line-of-sight connect. It must least likely violate by the original task controller you had. In other words, given the obstacle and the robot position, we can construct the current line-of-sight communication graph, and we may want to maintain the optimal graph, which are global and subgroup line-of-sight connect. With this, we provide our control revision strategy. Given any task-related controller, we seek to minimally modify it, satisfying the safety control constraints and the line-of-sight connectivity control constraints prescribed by the optimal graph and the control bounds. Finally, we make our algorithm as a functional block. Given any task-related controller UI head for each robot and go through our algorithm, we will give you the desired optimal controller UI star for each robot to maintain the desired safety and line-of-sight connectivity. And our method combines the global and subgroup connectivity constraints to enforce and control deviation from nominal controllers subject to the line-of-sight connectivity constraints. Then, we provide our simulation environment. Different color robots will go to different task regions and perform different tasks. We seek to minimally modify it to maintain safety and global and subgroup line-of-sight connectivity. The simulation results are provided here. On the left-hand side, it is our method, which considers the line-of-sight connectivity and dynamically updates the line-of-sight communication graph. The red edges represent the optimal graph, which defines the active site of pairwise line-of-sight connectivity constraints. In the middle, it is MCCST method, which didn't consider the line-of-sight connectivity, and on the right-hand side, it is fixed initial optimal graph, which only maintains the initial optimal graph without dynamically updating the line-of-sight communication graph. The results are here. And in the middle, we will see the robot will easily lose line-of-sight connectivity. And on the right-hand side, it is over-conservative, and such robots could easily fall into the deadlock. In summary, in this work, first, we developed the novel line-of-sight connectivity biocertificates to define the admissible control space for pairwise robots to maintain line-of-sight connectivity. Second, by integrating the design, the controls constraints, and the graph theoretical approach, we provide the greatest flexibility for the original robot's motion with enforced minimally disrupting global and subgroup line-of-sight connectivity. Finally, we provide the theoretical proof for our method. If you are interested in our method, please stop by our poster. The poster information is given here. Thanks for watching.